Mars, the red planet, our closest neighbor in the solar system. For millennia, we've dreamed of it as the next step for humanity, a symbol of our drive to explore. But are we truly ready for this leap? Can we survive there where dreams fade into sandy dunes? Mars isn't just another planet. It's a test of our technologies, our bodies, our will to survive. Today, we'll delve into the real challenges we face and the strategies we need to build the first human colony on the red planet. The first thing that strikes you is the harshness of the environment. Martian atmosphere is 100 times thinner than Earth's. This means extremely low pressure, making human life impossible without pressurized suits or specially controlled habitats. Extreme temperatures. During the day near the equator, it can reach 20 degrees Celsius, but at night, especially near the poles, they plummet to minus 125 degrees. These massive swings strain both human physiology and the materials we use for our habitats. And then there's the radiation. Mars doesn't have a protective magnetic field like Earth's. This means its surface is constantly bombarded by cosmic rays, solar particles, and intense ultraviolet radiation. This significantly increases the risk of cancer and central nervous system damage. Of course, we can't forget Martian dust. It contains toxic perchlorates, is abrasive, and can penetrate equipment and even our lungs. Global dust storms can last for months, blocking sunlight and making outdoor activities difficult. Even if we overcome the external environment, our own bodies face serious problems. Prolonged exposure to microgravity during the journey, and then the lower gravity on Mars, about 38% of Earth's, leads to muscle atrophy, bone loss, and cardiovascular deconditioning. We'll need regular exercise and special medications to combat this. But it's not just our bodies that suffer. The psychological aspect is just as important. The distance from Earth, isolation from family and friends, living in a confined, unfamiliar environment, all this creates immense stress. It can lead to depression, learned helplessness, and diminished crew cohesion. Group dynamics under the pressure of stress and limited personal space can also become a source of social conflicts. We need careful crew selection, effective psychological support, and clear rules for living together. Building a colony is a massive engineering challenge. We can't just bring everything from Earth. A key strategy is using local resources, in situ resource utilization. Martian soil can be used to 3D print habitats and create other building materials. This significantly reduces transportation costs. Energy is life on Mars. The planet receives significantly less sunlight than Earth, and dust storms can block solar panels. We'll need a hybrid energy system, combining solar, wind, and possibly nuclear power to ensure critical systems keep running under all conditions. Life support systems must be completely closed loop. We need to efficiently recycle water and air, using both mechanical and biological processes. This is crucial, as resupply from Earth will be extremely difficult and expensive. Establishing a sustainable colony on Mars is as much a socio-political challenge as a technical one. Current international space treaties provide only a basic framework for activities on celestial bodies. They don't address the complexities of long-term settlement, resource extraction, or the rights of colonists. There are also ethical questions. How can we protect Mars from Earth microbes? And do we have the right to change the planet's nature to make it more like Earth? These are questions for long discussions and careful study, ensuring reversibility and planetary protection. Surviving on Mars and ultimately colonizing the planet demands addressing a multitude of real problems. The environmental challenges, the physiological and psychological stresses, and the technical hurdles of creating sustainable habitats are formidable obstacles. However, a multidisciplinary strategy that integrates advanced architectural designs using local materials, closed-loop life support and resource utilization, diversified energy systems, health countermeasures against radiation and microgravity, and robust governance structures holds promise. Combining these strategies, as evidenced in numerous modern proposals and studies, suggests that while Mars colonization is undeniably challenging, carefully orchestrated technological, biological, and social innovations can enable human survival on the Red Planet. Only through integrated interdisciplinary research and international cooperation can the multifaceted risks be mitigated, paving the way for a sustained human presence on Mars. Overall, the roadmap to Mars survival is not linear, but an intricate network of solutions that must be iteratively refined through simulation, analog missions, and ongoing scientific inquiry. With continuous improvements in habitat design, energy production, agricultural systems, and human health management, the vision of a self-sustaining Martian colony transforms from science fiction to an achievable long-term objective. By addressing both the immediate and long-term challenges, from pressing environmental extremes to the evolution of Martian governance, we set the stage for humanity's next giant leap. Ensuring that survival on Mars is approached as a comprehensive, multi-dimensional endeavor. Continued research, international collaboration, and the integration of diverse fields of expertise are essential to overcoming these obstacles and realizing the goal of long-term human survival on Mars.